Amine has left me all alone. He's moved to the right side of the room to present his work, which was the winner of the best student paper competition. Amine Bennouna is a fourth-year PhD student at the Operations Research Center at MIT, advised by Professor Barton Paris. Prior to joining MIT, he received a Bachelor and Master of Science in Applied Mathematics from École Polytechnique. His research interests lie at the intersection of machine learning and optimization, with a focus on developing novel, robust, and reliable machine learning and decision-making methods. Let's all welcome Amine Bennouna.
Thank you so much, Kim. I hope that my speaking skills will match my hosting skills with Kim. We'll see about that. Thank you so much for the opportunity to speak at the ORC seminar. It's very much an honor, and also an honor to receive the award. We've been rehearsing Kim's French skills to say École Polytechnique, and it was worth it. It was very much said right. Okay, so I'll talk to you today about robustness in data-driven decision-making. We'll try to understand why we need robustness in data-driven decision-making applications, how do we define it, and how do we achieve it. And this is going to be hopefully very clear by the end of the talk what I mean by all these terms. Okay, so we'll consider a general setting of stochastic optimization where we have some set of decision theta, some uncertainty following a distribution P, and a loss function. And the goal is to optimize the expected loss over this distribution. So this really captures a broad range of applications, and throughout the talk you can keep in mind your favorite application. So one example is a news vendor problem, for example, where the xi here, the uncertainty, is the demand, and theta is the inventory. So you're going to receive customers who will have a certain demand that will depend on various things. Maybe today there's sales, maybe there's other things happening tomorrow, and you want to order just the right quantity given your demand. So this will depend on the probability distributions, and you just want to have the right demand to maximize your profit or minimize your loss. One other example is, say you want to schedule some nurses in a hospital, and you want to schedule them depending on your patient's arrival rates, which we assume follows some distribution P. So you just want to have the right number of nurses to satisfy the demand of patients, so they don't wait too much. But also you don't want to have too many nurses, so many of them are just sitting and doing nothing. So this also can be modeled as a stochastic optimization problem. And an even more broad set of problems is machine learning. So think of your favorites model, linear regression, neural networks, or decision trees. And then your data follows some distribution P. And what you want is to minimize the loss of your model. Okay, so throughout the talk, whatever I will discuss will apply to all these settings and virtually any stochastic optimization problem you might have. So you can keep this in mind, and it's going to be useful for illustration. Yes, Professor?
Is the probability distribution part of the input? Is it known?
So this is exactly my next slide. It is unknown. So this is practical applications. The probability is not known, and you just have data. So in all the talk, we'll never use these probability distributions, and we always only use data because in practice, this is what we have. So for example, I want to train a neural network on images of dogs and cats. I cannot really say this follows a normal distribution or whatever. Usually you have no idea about the distributions, and even most of the time, you don't even have a parametric family of distribution. You really just have data, and you want to make a decision out of it. So that's the challenge, is to estimate this expectation that is unknown because you don't know the distribution, just using the data. And the question is really, what is the right way to approximate this expectation? Okay. So perhaps the most straightforward and maybe naive way to do this approximation, and yet probably the most widely used, is sample average approximation, or empirical risk minimization. So you have an expectation and you have data. And so you just replace the expectation with the empirical counterpart with the data points that you have. So the question is, how well does this perform, even though it was used for so many years? And the answer is not so good, actually. This is what is known as overfitting. It does not really perform well. And moreover, you don't really have guarantees on the outputs you have. So sometimes it will perform well if your data is nice and clean and everything is well set. But if your data is not really prone to such method, it's not going to perform well. So keep in mind this problem of guarantees. This does not really give you any guarantee. So problems of SA and ERM has been documented a lot in many other literatures, has been also called error maximization effect or optimizer's curse. The question is how to overcome overfitting, how to have strong and robust decisions, and the answer is we need robustness. So we need a way to make robust decisions, some decisions that perform well, but also gives us some guarantees on the outputs. Okay, yeah. Yeah, so, perfect. I did not agree with him before the talk. This was completely... So the question is, what is actually overfitting? Because this is a word that we use for so many things, but it's not always the same things. The question is, what causes overfitting? And here, what we try to do in our work is to really understand precisely what we mean by robustness, what we mean by overfitting, and to categorize things. So the first reason, and perhaps the most fundamental that you can never escape, is what we call statistical error. So this is that even though your samples might be realizations of this unknown distribution, these samples are random and fluctuate, and if you fit too much to these samples, you will not really have the optimal prediction, but you have something that overfits to the data in that sense. And that's the most conventional meaning we give to overfitting. So that's what we'll call statistical error, or another way to call it is generalization problems, essentially. The second source is noise. This is also widely studied, and that is you have a small perturbation on your data, and this might completely fool your output. So there have been a lot of work on deep learning about that, and you can show that a lot of models, whatever they predicted first, you can always change it with a small noise that you do not really perceive, so you still have the same image, but you change the prediction, which means many models are very weak compared to noise and very susceptible to noise when you just use ERM or SAA, for example. And the third source is what you call misspecification. So this is some of the samples are completely wrong, right? So do not really follow your distribution. So one example, I thought I might mention ChatGPT in my talk, is if you ask ChatGPT if the Earth is flat or round, then ChatGPT looks at its training set, so the internet. For sure, it will be a lot of data point that tells that the Earth is flat, and you don't want it to tell you the Earth is flat. You want it to kind of generalize well in that sense. You want it to be robust to these few data points that are wrong. And I hope I did not offend anyone in the audience if the belief was different. But so this is just a fun example, but there is more realistic and an important example. For example, lately there was a team that took conventional spam filters, the state-of-art spam filters, and just changed the labels of some 1% of the emails that they trained on, and they showed that they can make their error arbitrarily bad. So this is very much a problem. Yes?
Do you mean by noise, do you mean that small perturbation on the X and the specification essentially noise on the Y?
So both of them can be both in the X and Y. So here I took the example of X, but the difference, and that's actually a good question, what's the difference between these two? So this is a small perturbation of all the inputs, right? While this is arbitrary perturbation on hopefully a small portion of the data. Right? I mean, of course, if all your data is completely poisoned, you cannot do anything. So you assume you just have few data points that are poisoned. But here, noise can touch all your data points. All right? But the assumption is that it's relatively small. Yes, Professor?
I guess I don't quite understand what you mean by the difference between statistical error.
So statistical error is, say you have just IID samples that follow exactly your distribution. So these are just samples. But noise is you sample, but you perturb each input with noise. So when you see the samples that are noisy, there's a distribution shift. They do not really follow your original distribution. Okay? So here, we're interested only on the sampling error, but here, each data point is also moved slightly.
Thanks.
Okay. Yeah.
The way you talk about it, you seem to believe that there's a probability distribution as ground truth, that it governs the story.
Yes. So that's a good question. That's very much something that is debatable. So we take it as the assumptions of stochastic optimization, that you assume there is some distribution that somehow governs the ground truth. But the key difference here is that we do not use this distribution. We just assume that it exists, and it somehow gives us a theoretical framework to be able to say things. But that being said, it's very much a debatable question. Yes? Yeah, that's a good point. So statistical error is typically something you can get rid of if you have large samples, but noise is something you can never get rid of. Even if you have a lot of samples, noise is always going to be there. Okay, so here in the first part of the talk, let's focus first on the unavoidable problem that is in any application you consider, that you have this notion of statistical error. And let's forget about these, what we call corruption, both of these. And I should also remark that we mentioned these three because they're very relevant in application, but you can imagine like more other sources of overfitting that I will talk about a little bit later. So more precisely, what is statistical error? It's the difference between having the ground truth, so the true model, and just samples. Okay, so that's this part. So we'll talk about robustness for the IID. You have IID settings, all the data points is clean, so what should you do? So the problem is you want to approximate this stochastic optimization problem. You don't have the distribution. And what you want is to construct some approximation that uses the sample. So this is the empirical distribution of the samples. And this is the model, right? So you want to construct some function of that. And some examples are ERM, which is you just take the empirical distribution, the empirical expectation, or regularization. So this is lasso, ridge, and this is also widely used. You just take the empirical expectation, and you add to it some regularization with some lambda maybe here of your model. And one other a little bit more elaborate one is distribution robust optimization, which we'll talk more a little bit later, is that you take some worst case approach over distributions in some sets around your empirical distribution. But we'll talk about this a little bit more. So with all these existing methods, the question we ask is which one should you use, which one is robust, and which one is the right for your specific application. That's what we'll try to investigate. And to understand that and to answer this question, the first step is to understand what is robustness and define rigorously what we mean by robustness. So by robustness in data-driven decision-making, what we mean is having a guarantee on your out-of-sample performance. So whatever in-sample approximation I will construct, say maybe ERM, I want it to give me a guarantee on the out-of-sample error. And when we survey all the papers on machine learning and operations research that construct approaches to stochastic optimization, they always give guarantees of roughly the same form, which is something a little bit like that we want the in-sample error, so this is the whatever in-sample error you constructed, maybe lasso or maybe ERM or whatever we constructed, we want it to be an upper bound on the out-of-sample error. That is, whatever I measure in sample, I want it to give me a guarantee about how bad it can get out of sample. So whatever I get out of sample is at least as good as what I have in sample. Okay? This is an important concept. So usually guarantees that you find in papers are something like that, plus maybe some constants. But it doesn't really matter because these constants, you can also put them inside here.
What do you call it out of sample error? This is the expectation over an assumed probability distribution. Where is the out of sample data here?
So the out of sample data is the data that's going to follow your distribution. See here, I take my loss, I evaluate it on data that follows my true model. That's why I call it out of sample. So this means when I...
This is not the out of sample empirical measure, for example.
Yeah, so the out of sample empirically is going to be just the empirical version of this. But this is somehow really what we really want. So this is what when you do this empirical, this is what we really try to approximate. So whatever model I learn, theta, when I deploy it in the nature, that's the error I'm going to get. Because my data flow in nature will follow this distribution. And so this is what I will get. OK, so I want that my out-of-sample error for whatever model that I learn is guaranteed to be at least as good as what I estimate in sample. And that's the guarantee that I want. Now, there's a random variable here, which is the data, empirical distribution of the data. So to make this rigorous, I'm going to take a probability of this event, and I will say it's going to be high with high probability. Okay? And then I can quantify the strength of my guarantee with this term here, with how high is this probability, this AT here. So if I want to be sure that my decision is very robust, so I'm certain that it's going to perform as well as what I estimated in sample, then I will choose a very high AT. And if I'm fine, I just want performance, but I really don't care about robustness, then I will choose low AT. So I don't really care about this upper bound, and I just care about the performance at the end of the day. Okay? This is how we define somehow rigorously robustness, and that's just somehow taking whatever exists in the literature as guarantees and putting it into kind of one framework and saying what we mean by robustness. And it's also, this is important in machine learning because it gives you a certificate of your solution. And whatever I learn, I present it to doctors or company CEOs, and I will tell them this is my model, but I can tell them with a guarantee that this is how good my model will perform. Okay? So this is very much important in practice. Okay. So I just want to give you some visualization of what's happening. This is really just a sketch. Say this is my out-of-sample error that I want to approximate, but I don't really know. And that's my estimation that I construct. So this estimation fluctuates with the randomness of the data. And I want whatever fluctuations, the high probability fluctuations, to always be an upper bound on my out-of-sample loss. And what I want to avoid is to have something too close to the out-of-sample. And so I would have these bad events, which is I underestimated my error. And I'm going to have something that will look good in sample, but out-of-sample will be very bad. So now the question, OK, I have my guarantee. Now I want to construct a robust algorithm. And before jumping too fast on what exists, let's say, can we construct the least conservative robust algorithm? Now, obviously, if you just want a robustness, you can just have a large in-sample loss, have a huge regularization, then you're very robust. But it's not really what you want. You want something not too conservative. So there's a trade-off there. But the question is, what is the least conservative formulation? And it's kind of a tough question to answer to, because if you have two approximations that somehow look like that, then clearly this one is better. It's less conservative. It's not too much of an upper bound. But if you have something like that, you cannot really compare it with the two others. If the data realizes somehow here, then you're better for the green one. But if it realizes here, then you're better for the blue one. So which means it's unclear if there is a model that's universal, always better for everything. Yes, Professor?
I recognize that this is a valid objective. But if you think of the problem, I would say a notion of robustness that looks satisfactory to me, anyway, is that the arg-min, you are trying to find expectations and so forth, which is a hard topic
yeah.
You're about to embark on it. But what you would like is the theta star that you find by solving an approximate problem and the true theta, the truth, that they are close. I would say that's pretty important.
So that's an excellent question. Actually here, what I'm showing you is somehow the simplified version, but in the paper we do look at the theta star. And we look at all these, whatever I present you here, replace everything with stars, and everything that I'll show you will hold eventually. But I'm kind of, yeah, exactly. And I'm kind of showing this just because it's easier to see. But in the paper, we actually look at, because you're right, so somehow we started with this, but then we thought what really matters is the optimal solution and how close. And actually, things generalize hardly mathematically, but it's actually generalized. So the proofs are complicated, but it's hopefully, luckily it works. Okay. So really what you want, the least conservative, is something that would look like that. That's really just an upper bound given the fluctuations. So we find a very nice, at least for me, very exciting results. And quite surprising is that there exists some formulation that is uniformly less conservative than any other formulation, which means whatever your model, whatever your data size, whatever your distributions, this will always be the least conservative that verifies these guarantees. And we can explicit them. It's interesting because kind of find a phase transition. If you want strong guarantees, which we say AT is roughly T, so your probability there is exponential. So you're exponentially fast decreasing the data size. Then the best thing you should do is distribution robust optimization with the KL divergence. And I'm going to give in a minute why this kind of makes sense to find here in this theorem. And then if you're...
Uniformly less conservative, what does it mean?
Which means whatever your ground truth is, and whenever your realization of your data is, this is going to be less, so this is will verify, of course, this guarantee, but it will also be less conservative than any other thing you construct that verifies this guarantee. Which means if you verify this guarantee, you cannot be smaller than this quantity for whatever empirical distribution, for whatever ground truth you have, also for whatever model you take. So conservative is, say you take a large regularization. So you're somehow... So which means this probability is, so this probability is verified, but this orange part is going to be too big. So because, one easy way to verify this probability is just to take the orange part, which is the in-sample cost, too large, right? And you're sure you're going to verify its probability equal to 1. So for example, if you take empirical, so this is an expectation, you take its empirical version. Yeah. Yeah, you want somehow the tightest, your in-sample, you want it to be the tightest upper bound. Yeah. And in machine learning, think of it as this is what you want to minimize, the tightest upper bound of your true loss. So then if you want weaker guarantees, think of like this quantity there, polynomial, for example. So AT is very small compared to T. Then what you find is the best thing you should do is empirical risk, so SAA, plus penalizing with the variance, the empirical variance. So that's kind of interesting because the folklore is to use lasso ridge. But if you just want generalization, then the right thing you should do is actually empirical. So this is standard deviation. This is what you should penalize with if you want generalization. But yes? Yes, for all theta. And again, this also is true if you take argmin everywhere, if you replace this with theta star.
So is the all theta inside the probability or outside the probability?
Oh, okay, this is a good question. So here I'm requesting it outside of the probability. Yeah.
Can you repeat the question?
So he says, do you want, so this is actually a very good question. If you want this probability to be true for every theta inside the probability or for every theta outside. So if you want this upper bound to be uniformly true. This is a very good question. So here, so far, I'm putting the for all outside. But give me a few slides and then we'll put it inside. Because actually putting it inside is very important. This is somehow the whole consideration of Vapnik and all this complexity theory. This is somehow why just this changing of operation. But we're going to discuss about this a little bit more. Yes, there is it's the same thing, actually. Yeah, it's the same thing, and there is even stronger connection. It's just how confident you want to be. It's kind of the lambda that you will put in front of the SCD or the variance. Yeah, I don't know the numbers exactly for UCB, but okay. Now I just want to give some intuition about why this KL divergence appears here. And think of, my true model is this red point. And then the data I observe, the empirical distribution, fluctuates around this red point. So what I want is to infer the true model from the empirical distribution. And there's this nice theorem by Sanov. This is just an informal version of it that tells you that the distance between the true model and the empirical distribution has always a bounded KL divergence. It's kind of the likelihood in a certain sense. And so this ball here is somehow a confidence interval around your data points that contain the true model. And you can actually show, it has been shown with large deviations that it's somehow the tightest confidence interval that you can construct. Okay, I need to go a little bit faster. So now this is about generalization statistical error. Seems like, we solved the question that we asked before. But yes?
Practically speaking.
Yeah.
You have data. The nearest example that you said, you have arrivals historically. How would you use this to inform the robust against statistical error using this theory? Maybe it's not the right time to talk about practicality.
Yeah, so I'm not sure I understand well, but so you mean basically how do you use this to actually give practical insights? So basically, I would ask my practitioner. So also we'll talk about practicality a little bit later, but already I can give some more intuition. I can ask my practitioner how confident you want to be about your prediction, right? If you say this is a critical application, I want to be 100% confident, then I will increase this AT here. So I want to have this high robustness auto-sample guarantee. I will increase it, and this will give me, some prediction. And I can tell that my prediction is the same as what I give in sample in my slides to the company with the probability that I will compute with this 80, right, with 95%. I'm confident 95% about my prediction, right? But then my prediction will be kind of suboptimal because I'm too robust, too conservative. Now, if the decision maker will say, no, I just care about, my expected profits, and it's fine if you make mistakes from time to time, then I will take a lower 80, right? And then I will say, I'm confident 50%, but you kind of get good results from time to time. So somehow this is the practicality. Yeah, all distributions around the data. Yeah, we'll talk about tractability in a minute. But this is a very good question because as a first approach, this is very much not tractable because these are continuous distributions, kind of an infinite dimensional optimization problem. But we'll show that it's actually not that complicated. Okay, now we talked about statistical error, clean data, but this is not reality. Reality is data is always noisy. There's always corruption involved there. So what about noise and corruption? Whatever I showed you before, how well does it perform if I am in the presence of noise and corruption, so in real life? And the answer is not so good. This scenario can very much still happen. Actually, the KL divergence is kind of a frail object with respect to noise. You can always find some smart adversarial noise that's completely blow up your prediction. So this is kind of interesting because the early statistical and machine learning literature, they focus on this sampling error, and that's somehow the sole focus. But here it shows that focusing on sampling error alone, statistical error alone, is very much not enough because this is quite a different dimension than noise. It's two fundamentally different problems. So, so now kind of I go back to my first slide, and then I say, okay, now I have to consider noise as well, which now I formally define as small perturbations, so bounded perturbations to my data. And then misspecification, which is some data points are completely changed. Yes? It's a good question. So here we'll say noise can be anything adversarial. Take it like adversarial, so it depends on the data, it depends on everything. So an adversary chooses your worst noise. But this is a good question because that's somehow going to be the main limitation of this work, is that if you know more about your noise, then you probably can do better. But here, why kind of we started with this because it seems to be the more realistic in many applications that you don't know much what's going on in your data, right? You just know that it's not too noisy, and so it's kind of bounded noise, right? Or it's too noisy, then you can say it's larger noise. But if you have more information, then you can do probably better. No, you assume nothing about the noise, just that it's bounded. So it can be adversarial in that sense. Okay. And now, really, I think one of the main takeaways that I think is interesting about this work is that what we want to see here also is how these interact between themselves. So most existing literature, as I'm going to show you in the next slide, consider one of these, but what happens is that when you consider the three of them at the same time, they somehow interact. Say an adversary can select your noise, can corrupt your data points, and then also statistical is present, so the noise will play with statistical error to fool you the most, and same for misspecification.
The first and the second are not compatible. If you have IID, how come the sum of the epsilon squares is less than delta? What way do they interact?
So how we assume it happens the following way. First, you have the data that is sampled, and then an adversary comes. Yeah, you have further noise, and then you have further corruption. Okay, so what did people do before? So there is classical region lasso, which is also equal to the same thing as robust optimization. or what is called adversarial training in the machine learning community. So this is, in a sense, it seems you can interpret it as something targeted toward noise. So you see here that we're considering the worst noise perturbation of our input. So really we're protecting against noise in a sense. I'm not really caring, at least directly, about the two other sources. So maybe it does protect against the others, but we don't really know. At least it doesn't seem to be designed for that. Now there's this two that I showed you earlier, so KL divergence, variance penalization, which is targeted towards statistical error, as we've seen before. And then one other example is Wasserstein distribution robust optimization, which can be shown to be just you take in some adversarial noise, but that is bounded in average, so some type of noise. So it's also, in a sense, can be interpreted as designed to protect against noise. And now the question is, let's take, for example, robust optimization. The question, or adversarial training, the question is, well, how well does it perform in protecting against statistical error? And here there's a very nice paper that appeared 2 years ago, and actually has now 500 citations in 2 years. It kind of created the whole subfield of adversarial training. So they did this experiment. They trained a neural network first with ERM, right? So this is the standard training. This is the in-sample loss. And then they tested. This is the out-of-sample loss. So that's some of the regular one-on-one training. It's kind of, this is what we expect from neural network, that the error, it doesn't overfit in the sense that the testing error never really increases. I mean, if you do it with linear regression or any other model, the error will eventually increase and you overfit. But neural networks, they have this strong generalization that whatever you train, usually it doesn't really increase and you still improve with more training. Now, they did the same experiment, but with robust optimization, so adversarial training. And what happens is that you start actually overfitting, right? So this strong generalization of neural network disappears with robust optimization. And then the gap you get, so the in-sample, out-of-sample gap, the generalization gap, becomes much larger with robust optimization. There was a lot of subsequent work that tried to explain empirically at least why and try to overcome it, find ways to regularize more robust optimization to overcome it. But the main remark is that it's still very much present. And lately, we actually could prove that this thing is not surprising. Yes, Kim.
What method was used for this robust training?
So this was, this was the classical Maggi approach that they use for that. But I think, if I'm not mistaken, this kind of works with any approach that's try to solve this problem in deep learning. Okay. And so we could prove that this is not very much something surprising, and you're going to show this result theoretically that there is kind of this gap. And the intuition is fairly simple. Is when you do robust optimization, you kind of have some two-layer of sampling that happens there. First, you're sampling your data points because you're computing an empirical expectation. But then the noise also is somehow in sample, because the noise you consider is the adversarial one to the data points, which might not be the same as the out-of-sample noise that you will get. So there's somehow two layers of overfitting that happens with robust optimization. Now, this doesn't mean robust will perform worse than ERM. Maybe it will perform better. But why? It's just because it does give you bonus because you protect against noise, but you might lose a little bit because of statistical error. And actually, in the paper, we give some examples. We construct some classification examples by hand, where we show that sometimes you pay too much on statistical error, that the gain is noise is not enough, and ERM is better than robust optimization. So somehow, targeting only noise is not really enough to protect against statistical error. Okay, so now the natural question is, can we actually protect against all these sources of overfitting simultaneously? And we want to do it in the least conservative way, right? You can always be too conservative. And then we want tractable formulations, as you mentioned earlier. Okay, so now I'm going to present you a method that will kind of try to address all these problems. But before doing so, I wanted to give some intuition about why what I'm going to present next actually works. So say this is your true model, right? This is your out-of-sample distribution, right? This is how your real life, this is nature. Then how do we assume the data is generated? First, you sample. So This Q hat T is your empirical distribution of clean samples, so that's your clean distribution. And then some adversary adds noise and misspecification, and then you get what you observe, which is the corrupted samples. Okay? So the challenge is, how do you infer the true model, so the true out-of-sample distribution, from the corrupted samples that you observe? And what we want is to have some distribution robust optimization approach where we construct some ball around my observed samples, so the red points there, that contains the model with high probability. So we kind of want to construct some confidence interval that is big enough to contain my true distribution with high probability. And then what I will do is I will optimize the worst case expectation over all the distributions that are in my ball. So because my model is in this ball, so with high probability, I will be also optimizing an upper bound on the out-of-sample error. Okay? That's some of the intuition. Now, how can we construct such a ball? Oh, and one more thing, we want a ball that is not too large, in the sense that if it's just slightly smaller than our constructed ball, it would not be robust, in the sense that there's some realization of the data in which this ball is not a good confidence interval, so it does not contain my true model. Somehow we want just the tightest ball. So how do we do that? And the idea is to kind of quantify the distances between these distributions that I showed here. So on one hand, you have the out-of-sample one, the model, clean samples, and corrupted samples. So first, the distance between corrupted samples and clean samples. And actually, we can construct a distance between these distributions that characterizes what is add-in noise and misspecification, which is, from the famous Levy-Prokhorov metric, somehow a generalization of that. We don't really need to see the definition, but we need to see that this definition here allows us to have this characterization that this metric here quantifies exactly what it means, that two distributions are bounded by a noise, are different just by adding noise bounded by delta and less than alpha% of corrupt data points. Okay? So we constructed this distance that tells you whether these two distributions are really different by noise or misspecification. Okay? So we have a notion of distance between corrupted samples and clean samples. And so I can construct a confidence interval around my data points that contains the clean samples with high probability. Okay? And this is this ball here. So it characterizes all the possible clean data points knowing my observed corrupted data points. Now the next step is the distance between the clean samples and the model. And that's what we've seen earlier, which is the KL divergence with Sanov theorem that tells us that likelihood allows us, so this likelihood KL divergence allows us to measure how far is my true model from my observed samples. So this is with KL divergence. So my initial ball, I can just inflate it with the KL divergence, and then I get the ball that I wanted. So I can construct my predictor, as I mentioned earlier. This is just writing the ball that I have and optimizing over the worst distribution in this ball. And we call it HR as holistic robust. Somehow we want to consider all the robustness. Ask me now a question, because I need to drink. So I use it. Yeah, it's a good question. Actually, we'll talk about how conservative it is. So although intuitively, why this should not be too conservative? Because whatever ball I constructed is somehow tight in a certain sense. So given what I observed, so in my slides the balls look big, but they're actually not so big, mathematically. So kind of this. So this orange ball contains, given my adversarial noise, I can really be anywhere in this ball. And I will see this actually rigorously in this result. So what you can prove is that if you have a noise that you know is bounded, and you have a certain number of corrupted samples, and you know it's not above that, then you can show that this predictor, this formulation, this in-sample loss, is an upper bound on your out-of-sample loss with high probability. And here it's uniformly. And for who asked the question before, now you have a uniform probability. So, something interesting happens here, because usually to have this uniform bound, you need some notion of complexity, some VC dimension, some Radmacher complexity or something like that. But here you don't really need any of this. And actually this bound, so okay, it's with high probability. I have a small O of 1, but this is usually finite. It's actually a finite sample. But also it does not depend, and this is quite an important point, is that this does not depend on the dimensionality of your models, of this set theta. It does not depend at all on that. And this is important for deep learning because your model, the set of neural networks, is usually very highly dimensional and even more highly dimensional than the data itself. So if you depend on it, if you have a bound that has some complexity of neural networks, then your bound is practically not very useful because this complexity term is just blowing up and is very large. Okay? So the fact that we don't depend on dimension is quite important, and it kind of gives hope that this theory is applicable in practice. And actually, it will be, as we will see. This is somehow the thing that really allows you to see these theorems in practice. Okay, and then the trade-off that you pay, I mean, nothing is for free. The trade-off is that now you depend on the dimensionality of the data, right? So this here will depend on the dimension of the data, say like your number of pixels, but not on the size of your neural network. And we also can show that this is tight. This is has optimal robustness. This is, again, uniformly smaller than any other predictor, any other formulation that's verify this robustness guarantee. So any other thing you can construct that has these bounds will necessarily be more conservative than this formulation. Yes?
Trying to see what you're presenting here, how is it related to this literature on bandwidth with corrupted data points? And then usually over there is data, let's say it could be originally it was supposed to come from some distribution, and then but there are some part of the data set that is corrupted, not everything, but then and there's a budget on the overall level of corruption. And then usually if the level of corruption is sublinear, there's a way to design algorithm-based sublinear reverter. But as the level of corruption becomes linear, there is this impossibility result that we cannot get sublinear reverter. So I'm trying now in your theorem you have this alpha percentage of the data point being corrupted, which is kind of that means that you have linear level of corruption in your data set if I think about it that way. So and then I know there is an impossibility result that you get a linear regret under such a setting. So is there a connection between this result and what you are saying? How should I think about that theorem?
So first, I'm not super familiar with this work, but I think I see roughly what's the problem you're mentioning. So one thing to keep in mind here, I'm saying this method will do the best that you can possibly do, right? In the sense that if actually you have, say alpha is 100%, I'm still going to be the best that you can do, but I'm going to do really, really bad, right? So this is somehow as good as it can get, right? But obviously. So here, we don't try to quantify how good you will perform actually, just because we know that any other algorithm will not do better than that. So we're saying the best you would be able to do, given this corruption, this is how you achieve it. But likely, this gap that you will have will be large depending on this delta and this alpha. Okay, I'll try to streamline a bit to get to the applications. So first, just the first remark, this, yeah.
So how robust is this thing through data? So if now you tell me if you know it's defined by
okay.
data, then
Okay.
I have all these things and all that. Well, I'm going to tell you actually it's data perception. Is this all going on the two?
That's an excellent question. First, theoretically, if you get larger delta than when you have, it works, right? Now, practically, you don't. So I will show you experiments later. We don't really know what noise is there. You just do cross-validation, and it kind of works. So in practice, you don't really know what's the right one, but you will see that it's actually not very sensitive. So I don't have these in the slides, but we can plot the error depending on how well you know the level of noise, and you see that it's somehow around the right number. It's kind of flat, in the sense that it's not very sensitive to that. But that's a very good question. Small remark that what we suggested, this holistic robust formulation, is a generalization of what exists already, which is if you just select this parameter, this is the noise parameter, non-zero, and all the rest 0, you recover robust optimization. So that's somehow a generalization for robust optimization. And same here, if you just want to protect against statistical error, you choose the right parameter, the corresponding parameter, you just get this KL DRO formulation that I showed you before. And for misspecification, you get total variance DRO, also CVAR optimization. But I'm not going to detail this too much. In the sense that this is somehow the natural generalization of what exists when you want to encompass all the sources of overfitting, or at least the ones that we mentioned. Okay, so quickly about the tractability. So as Dimitris mentioned, this is a highly intractable problem because it's a supremum over continuous distributions. You don't really know how to solve that. And actually, there was a paper in 2006 that's considered a special case of this formulation, so something that you can show this is somehow generalization of it. And up to today, there was no way to solve it. They kind of just suggest some heuristics that solve a similar kind of closed problem. But we were able to show that, kind of also somehow surprisingly, that this supremum is attained in distributions of finite supports, and for supports that we know. And so this infinitely dimensional problem can reduce to a finite dimensional problem that we can solve. And actually, it has some very nice structure that I will show you right now. So yeah, I mean, maybe I should not detail this too much, but you can reformulate it as some problem with linear constraints and an exponential cone constraint. And it's essentially just taking robust optimization and reweighting the data points in a smart way somehow that you can get with this optimization problem. It has also a dual formulation, so you can get rid of the max and have just one min when you want to optimize it, which also I'm not going to go too much in the details. Okay.
I have a similar practical question to that. So, what in these two slides, until where does it hold if you have integer variables?
If you have integer variables. Okay, so this part here is unrelated to whatever you have. So, this is always the same. So here, so this also holds. Yeah, this also holds. Yeah, this totally also holds. Your integer parts will appear here in your decision variables. So, everything I show here does not depend on the decision variable, only in here. Yes, exactly. And then your integer is in the min, right? So it somehow preserves the tractability of your problem. It just adds some linear and exponential cone constraints. Okay, I'm glad I still have time to talk to you about the exciting applications. So we said, okay, let's try this approach. Let's see this theory, does it apply in practice? And some of this was a strong motivation when we did this, that, okay, we don't want to just have bounds. We want to have something that really works in practice. Because in statistical learning, there's so many theory, especially in deep learning, but when you do simulations, you don't really get that. You use theory just for intuition. You develop algorithms, and then you kind of hope it works well. So we said, let's apply to the least regular laws that we know, also the most widely used, which is neural networks. So we just use this main classical benchmark, CIFAR data set. This is image classification. So our loss now is going to be neural networks on cross entropy, so highly irregular. And then we will train the network by solving this problem, so this min-max. And remember, I have these three parameters of our method, which is R for statistical error, delta for noise, alpha for misspecification. And now I should say also a word about this is that the cool thing about this as well is that whatever parameters you have, you can really know how they impact your model. For example, in lasso, the regularization term, you don't really know what it represents in practice. You just try to tune it, but here you kind of know what it will make your algorithm do. So first, we try with just the parameter R. So here, I just want to be robust to statistical error. This is just KL distribution robust optimization. And this is what you observe. So here we train just ERM. And also, so we train on multiple subsamples, so we can evaluate how much we vary our performance, how much our performance vary when the data varies. So this is ERM. And then here we increase the parameter R. So first thing that we obviously see is that the performance improves significantly.
What is the y-axis?
This is the loss.
Loss over the training data set?
So this is testing loss. So this is somehow the out-of-sample error that we get.
Which is cross entropy.
Yes, cross entropy. So the loss gets better. And again, remember, I did not really sell you the fact that we were going to get the loss better. I just sold you robustness. But what's interesting is that just by being robust for neural networks, you significantly improve the performance. And the intuition behind that is that neural networks somehow inherently overfit so much that if you protect yourself against statistical error, you gain a lot by doing this with neural networks. And here, when we ran first this simulation, we were kind of surprised actually how good it did, how much it's improved over benchmarks.
Does this contradict the earlier plot that you showed us?
The?
You showed us some earlier plot that
I'm going to show you how this plot shows. But no, here I'm just plotting the performance out-of-sample that I get, okay? And I just show that it gets better. But then importantly, where the robustness shows, first, see the variance is lower. Here I'm kind of more confident about my decision because whatever the data was, I kind of always have somehow the same performance, while ERM, it varies significantly. So if my data was slightly different, I will get a different result. Okay, so I cannot tell my company, this is how confident I am, but I'm going to add a little bit more about that in a minute. Okay, now I'm just also showing the training loss. And you see that the more conservative I want to be, the more my training loss increases. And I also get better in testing. So even though it seems I'm kind of worse in training, well, I'm just conservative, my testing loss gets better. So now, if you were very careful in my first slide, you will say, well, this is not your theory, because your theory told us that the in-sample should be an upper bound on the out-of-sample. And I say, you're right, but here I did not use all my parameters, so I'm just using statistical errors so far. Okay? And now I use everything. So, and to Patrick's question, I don't know what noise is in my data. I don't know what's misspecification. I just cross-validate. So whatever I plot here is going to be cross-validation. Okay, let me walk you through this plot. So this is various benchmarks. Here is ERM. This is trade. So this is somehow, maybe I should say state of art, but at least one of the best performing in some recent competitions for protecting against noise in deep learning, so adversarial training. This is robust optimization, so adversarial training. This is KLDRO that I showed you earlier. This is DPA, that's a deep learning algorithm that protects you against poisonous data points. So each one was cross-validated with the parameters of the respective paper. And then at each training, I plot the training and the testing error. And again, the data I'm using here is a corrupted data with some noise and misspecification, but that I don't know. Okay? So what do we observe? First, so HR performed significantly better than all the algorithms. And the difference is actually very stark. I have numbers maybe in the next slide, but the difference is very significant. But then the interesting thing is that not only we perform better, but we do have this robustness idea that my in-sample error is actually a guarantee on my out-of-sample error. And some of this is, at least personally, something I've never seen in machine learning, that you actually close the gap between in-sample and out-of-sample. See, all of these methods, and that's classical deep learning, have this huge generalization gap. So your in-sample does not really tell you anything useful for the out-of-sample. But here, the in-sample is actually almost exactly, it's upper bound, but almost exactly what we get out-of-sample. Yes, Dimitris?
Validate over R delta and alpha?
Yes.
Because different R delta and alpha might give you very different environments. So exactly what happened? So you cross-validate it?
Yeah.
That's not a completely trivial question.
Yeah, that's actually...
How exactly did you do that, R delta and alpha?
So you do a grid of all the possible values, the values you want, and then you train for each point in the grid, and then you have some validation sets, and you just take the best performing.
And the same was done for the other method?
Yes, the same was. Everything was trained the same way. And actually, we take the same parameter for every. So each method, we take the grid that was given by the paper. So it normally should be the best thing. Yes?
What happens if on the y-axis one wants to look at the actual misclassification, not the loss?
Yeah, this is my next slide. I'm going to show this in a second. Yes?
Another question is, have you, for example,
like say ImageNet, that does not protect against robustness? Because sometimes what happens is that maybe your like generalization gap is huge, but then your out-of-sample performance is actually better.
So that's a good question. So ImageNet, ImageNet is the dataset or the architecture? The architecture. So the architecture is somehow independent of what I write. So all these methods are things you put on top of the architecture. So here when we compare them, we use the same architecture across the methods. So what changes is just how we train these architectures. So of course, bigger architecture is bigger power, but the gain that each training method will give you will vary depending on the training method. So of course, here we trained them with exactly the same architecture, which was ResNet in this case. Yes, please. Yeah, we tried Cypher and MNIST. We tried also ImageNet, but we didn't finish this yet because it's huge. But yeah, we have the same thing. So in MNIST, we have the same thing, although the difference is somehow small, but the more complex the data sets, the larger. So at least Cypher, we had like even more larger things, differences. But we tried for Cypher and MNIST so far. Yeah, so for the scaling, the computation time of this method is only 4% more than robust optimization, adversarial training. So really it's the same. Adversarial training is some of the most classical method. Whatever it's applied to adversarial training, you can also do for HR. So it can scale as much as what we have now scales. We do not really pay any computational price in that sense. You mean in terms of performance, or does it scale? Yeah. We didn't try it exactly for Sci-Fi 100, but what I'm saying is that you don't really pay any computation time compared to existing methods. So if our existing algorithms could generalize to any large data set, then this would also scale to any data set. In the sense that it's very tractable in that sense. Yes, Dimitris.
Does this translate to AUC if it's binary, I don't remember, or accuracy? That is that you have lost here, but what is the implication on...
Yeah, this is my next slide. So I hid it, but I can show it, yes. So this is the accuracy. Here, this is the mean. So okay, here I'm using kind of deep learning terms, but poisoning is misspecification, evasion is noise. So this is the mean error, and this is the worst case error. And the difference is very large. So you see that somehow these methods are all around 50%, and here we're at 36%. So the difference is very significant. And it's somehow intuitive. Just any of these methods, again, it targets one specific source. So this is misspecification, this is statistical error, noise here, nothing here, misspecification here, and noise here. And although you do validate them with their parameters, you take the best performing one, but it still cannot compete between a method that really adapts to all type of noise that you give it.
The experiment here is that CFAR has you can use some out-of-sample test data.
Yes.
God knows what poisoning and things. This is the data. You apply the method, cross-validate it on this data. This is what we are seeing.
So what we do?
Additional assumptions on the data.
So we corrupt synthetically the data. So we add noise, invisible noise, and then what we do is some of the labels, we change them. So 10% of the labels. So this we do it, but we don't carry this information, which means we cross-validate without knowledge of this information, of how much noise is there.
I understand, and it's reasonable as a test, but from a practical perspective, the data is the data.
Yes.
You don't know so you apply the method to cross-validate the parameters, no further poisoning. Does it make a material effect on accuracy, on AUC, and so forth?
Yes, definitely. So this is our experiments so far, definitely. But this is what we would expect in real life.
About 88%, my recollection of AUC, if I'm not mistaken. Applying these methods, does it make it 90, 95? 89?
So we didn't apply to clean Cypher, but we could try this as well. But so because our assumption is that Cypher, the raw Cypher, should also have some noise in it and some misspecification in it, right? But we don't have this experiment.
But you are
Yeah. So what we do here, to kind of try to address this, is that if you see these columns, they're different settings. So this one has, so I write statistical error, but any data set has statistical error, samples. And this one we add only poisoning, so we flip labels. This one we add only noise, and this one we add the 3 of them. But in each of them, I cross-validate the 3 parameters. So, yeah.
Hopefully you understood what I asked.
So what do you mean by home course then?
I mean, you take the data,
Yes.
the data set, and you synthetically change the data to illustrate the phenomenon. Which
Yes,
I
yes,
think
yes,
is
yes,
okay.
yes, yes.
I don't disagree with that. But what I would like, so this shows that the method indeed works. However, in the real world, you have data. You cannot, synthetically start corrupting it. You should apply the method on the original data.
Yes,
If
yes.
on that data it improves, it won't improve, then you have a very practical theory, I would say.
Yeah, this is a very valid point. So here it's a proof of concept, but you're. Yeah. No, you're totally right. Yeah.
It's not so just.
No, this is true. This is just.
Maybe the result will hold.
Yeah. No, you're totally right. This is the next step, and this is kind of what we're hoping for, is to try to use this in practice and then see actually how much we improve in practical data sets. But you're right, this is just a proof of concept, really. We're not getting to practical applications yet, but hopefully this will be the next step. Kimberly?
So I just have a question. So usually when you have, like, for example, noise in the data, it's performed after you have trained the network, right? So that you can adversarially do it for each method. So was it done like that for each method?
Yeah, that's a good point. That's a very smart remark. So either you add noise in test time or train time. We actually proved theoretically that it doesn't change anything to the theory. So these experiments are after, just because this was a deep learning paper. But
so the noised versions of the test set are different for each method?
I think we actually, add the same. Oh, no, okay, yeah. It's adversarial, so it's different. It's adversarial to the method, yeah. Yes, Professor.
So suppose in the real world you don't have statistical error, like you have
The whole model.
to assume IIDs and so forth. Assume that it's not correct to assume that. But you apply it anyway. You protect yourself against all 3.
Yeah.
But one of them, it's not there really. What are you losing by doing that? Nothing.
What do you mean by there's no statistical error?
You have data.
You mean that it's not IID?
That is, you make an assumption. You are trying to protect against CIs that are generated by probability distribution. Not only that, the data is IID. And you are trying to protect against this thing. But suppose it's not true. It doesn't,
Yeah, that's a good point.
That is the negative. That is the fact that you are doing it. It might be you are doing, nothing happens. It's okay. But is there a negative?
So that's a good point, because you know all of these parameters, then you should cross-validate on them. But you're right that you might select the wrong parameter. Now, in the applications, which is something not guaranteed by the theory, but it's kind of a bonus that we get, is usually we do select the right one. For example, we did experiment without noise, and it seems most of the time it selects delta equal to 0. But I have no guarantee about that. This is just a practical observation. But you're right in the sense that choosing the right parameters is very much a problem. This is very much an open question in that sense. But you're right, this might be a disadvantage. Yes?
Can you say something about the value of getting more data for the different methods? Because if we come back to the very first discussion, then this having more data will help with generalization, but not necessarily with the other error types.
Yeah, this is a good point. And actually what we show, so I don't have any slides here, but we actually perform this with different data sizes. So we subsample like CIFAR, and we try in different data sizes. And what we see is that the gap, so all the methods perform better, obviously, and the gap between what we do and these methods shrinks. So somehow we don't need robustness as much when you have more data. So yeah, and usually what you should do is that this R should be selected smaller. Because remember, this R was somehow a ratio over T, this AT over T. So the more data, the smaller R should be chosen. But again, the limitation is that you don't really know what R to choose. cross-validation is your best guess. Yeah. I'm taking 5 seconds. Okay. Just I take this question, and then my next slide is future work, I think. Yeah. Okay. Last question.
So I think it's like usually, I guess, for example, for your data where you can have warm starts, right? So in
Yeah.
a sense that you have already known like weight matrix before you just apply. So in a sense that how would your framework change if you kind of have some sort of trial of where the data starts in that distribution?
Where the theta is?
Data start. Because basically you have a warm start, right? So you
I
kind of
see.
probably know where this data start is.
So I think it doesn't change anything in the approach. It's just changing the optimization. But the gain you have would be the same as any other method. But you don't really gain anything in terms of robustness, at least in the way we do things. Okay, so we have an open source implementation of this package for robust neural networks. It's really adding one line to your code, and you get this robustness for free. It doesn't cost you anything in terms of computation, so please use it if you're interested. Okay, so like 1 minute about future work and kind of what's the continuity of this, and what's the natural question is, whatever I did here, and as Dimitri said, you kind of assume that you know somehow what's going on your data. You can know there's some bounded noise, you know there's some specification with some percentage, but in many applications you don't. For example, say you have a distribution shift, like this one, where you train a self-driving car in California, so the scenery is kind of like that, and then you test it in Massachusetts, so the scenery change. So yeah, sometimes it's better than that in Massachusetts, but so there's a distribution shift. Yeah, possibly. That's true. Yeah, I'm not selling Massachusetts much in this slide, but so here you do have a distribution shift. You see that the same concept is kind of there, but there's a distribution shift. Although intuitively, as a human being, I kind of see what's going on there, but mathematically I cannot write this. So constructing a method that generalizes well when I train here and I test here is very much a non-trivial question. It's a very popular question. Oh, yes. So the question is actually, can we learn this distribution shift? What we're trying to do now is try to learn on the data what is this distribution shift and try to generalize in that sense. So maybe learn some ambiguity sets. That's kind of what we're investigating now. And that's very much a question of interest. So this is called domain generalization. And I looked at a literature review yesterday, and there was over 200 plus papers in this literature review in this past 4 years that try to create some method for this. It's literally just creating a method that does this. And lately, last year, there was a paper by Meta people that took all the existing methods. So all the methods claim to have good performance. They took all of them. They created one unified benchmark, and they tried all of them. And it turned out that most of them perform worse than ERM, and very few of them improve over ERM. And the best method, and the table is still online, you can check it out, the best method has only 1% more accuracy than ERM when you do these problems. So that's very much an unsolved problem. There's a lot of interest. And companies, so we've been talking to companies lately, and they're very much interested in this. That arises in really various applications. And so there's a lot of opportunity there. Okay, thank you so much. Sorry for taking too much time.